Hello again. My name is Chase Henderson. Today I would like to dive back into what we had earlier discussion earlier of the current statistics of coronavirus in Oregon. In part one, we explored the data provided by covidtracking.com. We calculated the positive percentage, which is the percentage of positive COVID cases divided by the total tests conducted. Additionally, we calculated the death rate, which is the death over total cases, total positive cases. We'll assess that later in our research. To refresh ourselves, we'll be looking at data specifically for Oregon and comparing that a little with the national-wide data of corona cases. And we'll be focused on the date ranges of March 3rd until August 8th. Moving into part two, we'll be focused on goal 2, which is the development of a univariate analysis of the data. Then we'll segue into goal 3, which is to build off our models and develop a multivariate approach to our analysis. So without further ado, let's move into goal 2. Here's a visualization of the positive percentage data for Oregon. Oregon has done well maintaining a positive percentage rate below the national average. But with our predictive tools, we want to forecast on how to trend the short-term data on the 7-day trend and the long-term, which is our 90-day outlook. We determined in part 1 that Oregon data was non-stationary. It contains wandering behavior and slowly dampening autocorrelations, which led us to determine that differencing of the data was necessary. Same with the national data, though we will see that the national data in fact needed a second round of differencing in order to achieve stationarity. Here's our result from the high pass filter differencing the Oregon data. The same high pass filter was applied to the national positive percentage data to achieve a nice realization not dependent on time and lag autocorrelations, not exhibiting the dampening effect. Both the AIC and the BIC contain a P equals 4 and Q equals 0 in the top 5. The positive autocorrelations, or PACF, also suggest an AR model appearing to support the AR4 recommendation made by both the BIC and AIC. After we've identified the AR4 model as our ideal model, we want to test the maximum likelihood estimator and the Yule-Walker estimator to determine the best fees for our predictor. Here's the last 7 days and the last 3 months of our data look like forecasted with the maximum likelihood estimation. The Yule estimation looks very similar to the MLE, so we will have to turn to an ASE performance calculation to determine the more accurate model. Here we see a comparison of long-term and short-term ASE scores for MLE and Yule estimations. In this case, the lower score is the ideal one. So we will move forward with the fees provided by the Yule estimation. We want those blocks on there to be as small as possible. And in this case, that orange Yule one is our smallest one. To check our model appropriateness, we look at the sample plotted. Here we can find that the Yule estimation does in fact most closely represent the difference data on the right. For the national data, a second difference was done prior to model estimation. While the AIC produced a recommendation of a P5 model, the BIC recommended a moving average model of the first order. The BIC will shy towards the simplest model, which is preferred in this case for computing power and simplicity. The ACF, the autocorrelation for the national data, supports a moving average model of the first order. Comparing the AR5 and the MA1 models recommended by the AIC and BIC respectively, we see that, in fact, the moving average of the first order is much more accurate when compared to the AR5. Here is a look at what that MA1 model forecast looks like, as well as the theta parameter that corresponds to that predictor. Looking at the model appropriateness of the fit, we see that the MA1 is superior in mirroring the national data. With a simple AR model and MA model chosen, then we sought to build on our prediction strength by applying more complex computing tools, such as the multi-perception model, perceptor model. While the calculations are more complex, the MLP did not render better results than the AR model. The same can be said for the national data. When applied, the MLP did not outperform either of our more conventional models. Moving on to goal 3, we will now dive further into the model complexity to attempt to beat our baseline predictors. To incorporate additional variables into our models, we have calculated the death rate. This is deaths divided by total cases of coronavirus in Oregon. This data exhibited wandering and dampening behavior and was applied a first difference to make it stationary. It was then used to enhance our VAR model. The vector autoregressive selector determined a P of 10 was ideal, and we incorporated the death rate as an exogenous variable. The VAR did not follow closely with the realization or the autocorrelation, nor is the frequency table aligned with our data set, which gave us limited confidence. But when comparing the accuracy of the VAR data set, it performs well in the long-term and short-term comparisons. It outperformed both the MLE and Yule estimator models. When looking at a 30-day moving 30-day window, the AR4 model we considered the best of the univariate models competes much better with the VAR model in ASE performance. Particularly focused on the 60-day and 90-day, it achieved better scores. That's where the 2 and the 3 are on this graph. To add another layer of complexity, we created an ensemble inspired by the Yule AR4 model and the VAR model. Those predictions were averaged and calculated for accuracy, and understandably, this created a new model that performed second place at all stages of the 30-day moving window. Though the VAR and the ensemble have predictive power, we still recommend the simplicity and explainability, the AR4 Yule estimated model for future forecasting of this type. Thank you very much. I really appreciate your time. Talk to you soon.